what we want to do in this last couple of days is kind of tie a bit of a bow as much as we can on rivers and streams. And so there's let me just give you some tips on where some of the subject matter is coming from, and I'm not following this exactly, but from chapter 12, which is the so-called rivers chapter, we're looking at pages 396 to 405 and 407 to 408, something like that. And from chapter 13, 442 to 449. Here we're talking stuff on hydraulic geometry, a bit on floods and floodplain sedimentation, channel plan views and channel profiles, particularly with respect to downstream finding. Here we're talking about the role of climate variation, origin of strath terraces, and the so-called channel width problem, which is related to the hydraulic geometry stuff that I want to talk about largely today. So, with that, unless there are any objections, even if there are, whatever. Let's get going. So, let's just talk basics here for a second and deal with channel formation. We've got at least a couple of ways we could potentially form a channel. In one, we say we've got a big enough source of water, we've got a steep enough slope, and we've got a weak enough substrate that we can erode that substrate and concentrate flow in that eroded channel. Okay, so that would be a channel that is formed by erosion, but it is formed by that flowing water, right? I mean, on a very fundamental level, a river is simply water flowing downhill. And what it does on its way is what we call a river, in the sense that it carves a channel and so on. Now, there's another way we can essentially carve a channel, form a channel. Again, we've got a big enough source of water, we've got a big enough sediment supply, let's throw that in there. For sure, the right slope, typically one that's decreasing as we go along, and that will give us deposition of a new substrate and the concentration of flow in a self-formed channel. So this is in particular what we see on river deltas, alluvial fans to some degree, submarine fans. Okay, submarine channels are kind of the whole deal. A bit different than sub-aerial channels in terms of their geometry, but fundamentally, it's still water flowing downhill carrying sediment as it goes. And you did look a bit at, if you think way back to your first couple of labs, you did look at some of these depositional landforms on maps. In particular, when we're talking about that latter depositional sort of channel, that channel that is formed out of the sediment that is being carried by the channel, you get the natural levees that form, of course, floodplains, and larger, on the larger scale, deltas, fans, and so on. And arguably, we could argue that those are, in some sense, fundamentally different. But maybe not so much, and we'll keep that in mind as we go along in the next little bit here. Let's think about some basic questions, though, along the way, or to keep in mind as well. First of all, if I talk about water flowing downhill, having enough slope, having enough essentially shear stress to carve up stuff and or load to deposit stuff, what sorts of flows are we talking about? What are the formative flows for? What are the main main events? What are the what are the formative flows for these channel formation type processes? And in particular, one of the things practically we really want to know is what are the channel dimensions? How does, for example, the hydraulic geometry, what's that? That's worth writing it down. Anybody want to volunteer what I mean specifically by hydraulic geometry? Because I could have said channel geometry, right? But I didn't. I said something else. I said hydraulic geometry. So hydraulic geometry is the dimensions of whatever particular discharge we have that day, or whatever particular discharge it is that we're talking about. So, that's when I go out to Oak Creek and I literally measure the top width of the water, I measure the water depth, and I measure the water flow velocity. Now, if I do that at the discharge that just fills the channel, that is the so-called bank full flow, then the hydraulic geometry and the channel geometry are the same, kind of. And I say kind of because does a channel have a velocity? Not so much. A flow has a hydraulic, that's still kind of a hydraulic property still. We can speak of the velocity at that bank full discharge. So the hydraulic geometry is essentially equal to the channel geometry at bank full flow. But if it's not bank full flow, then it's whatever geometry of whatever discharge we're talking about, whatever we happen to cross, whatever it is that we're interested in. Okay. So we can ask, for example, in terms of channel dimensions or hydraulic geometry dimensions, how does the hydraulic geometry vary with the magnitude of formative discharge among sites? So if I look, for example, at bank full discharge and go around to a bunch of different places and figure out that bank full geometry, including, say, even velocity, if I can, that's what I'm talking about. How does the hydraulic geometry vary, for example, with bank full discharge or some other magnitude of discharge? And typically when I say I'm looking at the same magnitude of discharge at a bunch of different sites, how am I figuring that how is that magnitude the same if it's different, right? It's different discharges at different sites that I'm looking at. Well, specifically, I might define it as the bank full, which is essentially saying the channel formative discharge. I might also define it as a discharge that has the same recurrence interval at a bunch of different sites. So say the annual flood with a 1.5 year recurrence interval. That is that so-called 1.5 year annual flood is often found to be nearly the same as the bank full discharge on average. So that's a common one to look at. But I could also look at, say, the mean annual flow. It's different from the mean annual flood that I talked about last time. Mean annual flood was the mean of the series of annual maximum flood flows. The mean annual flow, or the annual mean flow, or average discharge, is simply, how much water spills out of the channel during the course of the year divided by the time, or averaged over the entire year. So that's a thing that we can look at as well. The other thing that we might want to know is, how does hydraulic geometry vary with magnitude of discharge at a station? So if I go out to Oak Creek, today, over this past weekend when it rained, if I go out during the next storm and so on, and I measure discharge and I also measure the hydraulic geometry, how is that varying as the magnitude of discharge varies? So that's a somewhat different question, right? Now I'm saying, and I can always engineer a channel to make that easy for me by making, a nice rectangular box type channel if I so desire. But typically, that's not so interesting, right? Or what I'm really interested in would be going to natural channels and figuring out how their widths and depths and so on change with the different discharge. All right. Now, most of the examples I will talk about or actually show you data from are the first sort. That is, among sites, how does the geometry change? How is the geometry different among sites? So remember, just keep in mind the distinction. All right. Now, is this I guess one question is this a difficult problem? I mean, I don't know if you have an idea of whether it's a difficult problem or not. On some level, it doesn't seem like it ought to be that difficult a problem. Let's say, because on some level, it's simply a matter of kind of balancing forces on some level. Well, let's think about this. So if we have, say, this channel is too wide. What do I mean by too wide? Well, if I have a real broad pan of a channel, fill that up with some water, and it's carrying some sediment. Well, if by too wide, what I mean is that at the edges, it doesn't have enough oomph to carry its load often enough to keep the channel from narrowing in. So if it's too wide, I'm going to say get deposition at the edges. And the channel is going to get narrower and deeper. Okay. Again, if it's carrying enough, well, let's say the rate at which it does get narrower and deeper is going to depend on how much sediment it's carrying. You might also think of a channel that is too narrow. Sounding a little bit like Three Bears here. That's kind of what I'm getting at, I guess. So if I've got a channel that's too narrow, then I might actually have a greater shear stress at the banks than I do at the bed. And so I'm going to get erosion at the banks. And And so my channel is going to get wider and shallower. And if it's just right, then I'll get neither. Let me just say stable. Okay. That is, I'm not going to get erosion of the banks, or let me qualify that. I'm not going to get erosion at the banks and or deposition at the banks such that the channel geometry changes over time. Because an important caveat is that the position of this may change as I do get, say, deposition on one side, erosion on the other, and I'll get into that either today or tomorrow, but not tomorrow, Wednesday. Well, what are we talking about? Well, here that the shear stress is high enough to carry the load, but low enough to keep the banks and beds stable. Right, I've got enough to carry stuff. I'm not depositing anything over here. I'm not eroding here. Channel morphology is essentially stable. Now, as I said, real channels are not static in their stability. You might say it's a dynamic sort of equilibrium that we're looking at. Now, for example, erosional channels are going to be, say, cutting down vertically and often laterally as well. These channels are going to have geometries that are determined by carving out their substrates, although they may often be simultaneously deposited. Depositional channels are building up vertically and usually laterally as well. And these channels have geometries determined by depositing their loads, although they may be simultaneously eroding. And then we might have a few channels that are just neither cutting down nor building up, on average anyway. You know, they're essentially conduits for their supplied loads. But again, the channels are not typically static. They may be, typically they're going to be, say, eroding and depositing. So while the channel form may stay the same, at least on average, it may change in its location. It's kind of a little bit of an interesting mind exercise to think about. Well, it's not like the channel is picking up and moving over. And how are we even defining the channel? It's by that, I'm talking about simply the interface between solid material and the fluid that's flowing through it. So we can put a little more material here, erode a bit of material here. The channel has so-called moved. What's really moved is where the water is flowing and where the boundary between liquid and solid is. Because most simply, a channel bed and its banks are what's left over from the local mass balance. What's coming in, what's going out. And predicting the shape is, as it turns out, rather difficult. Because the details aren't so simple. I mean, it doesn't seem like this would be all that hard to figure out on some level. What's too wide, what's too narrow, what might be just right. In practice, it's been a bit of a knotty problem for geomorphologists to say come up with predictive models that can get the right answer, or physically based models that can get the right any kind of answer, any kind of model that can get the right answer has been a bit elusive. Now, that said, on the other hand, since the laws of physics are the same everywhere, and the range of conditions is finite on Earth, anywhere, there does tend to be some regularity, at least enough that empirical rules for hydraulic geometry can be found. So, in a nutshell, what are we talking about in terms of hydraulic geometry? What do I mean, or what are these, I guess really, what are the rules? What sort of rules are we looking at? Typically we are looking at expressing some hydraulic variable, like width, depth, velocity, as a function of discharge, specifically, usually a power law of discharge. You guys have started to get somewhat familiar with power laws, but if I'm just saying x is some variable, if I've got some hydraulic variable, I'm saying it's some function of discharge, and more specifically, some variable, some function of discharge. The typical form might be something like that. Again, this is the so-called power law. That is, got some variable. This might be width, depth, some other things even, proportional to discharge raised to some power. Now, of course, discharge is variable in both space and time. So for downstream variation, like I said, we choose for each place a discharge with that same recurrence interval. So we might look at a typical sort of flood, like a 1.5 year flood, or the mean annual flood discharge. For time variation, we'll look at relationships at a single place or at a station. So we can have both so-called downstream variation. That's when we're looking at the same magnitude, well, let me be more specific, same discharge with the same recurrence interval. Is that a term that is at all familiar when I say recurrence interval? I think I've used that term before. We get it, it's the kind of term that gets hydrologists in trouble a little bit when they start talking about the 100-year flood, which is why they don't do it anymore. If you listen to government engineers now, the Corps of Engineers, it's like kind of become policy not to say 100-year flood. They'll say the 1% flood. The flood with a 1% chance per year of occurrence. On average, that means the recurrence interval is 100 years, but it's people, when people hear 100-year flood and they hear recurrence interval, they tend to think regularity. When they hear something just like it's the one with 1% chance of occurring, that is a little more intuitive to people as to what we're really talking about. So that's what we really mean when we say recurrence interval. And then we've got the so-called attestation variation, where we're looking at discharges out of place with different recurrence intervals. Ri for recurrence interval. So the main relationships are the ones that, say, came up in the literature the soonest. Back in, I guess, 1953 is when the sort of landmark study by Leopold and I forget what's his name, Maddock. So typically, or at least the main relationships that we're looking at are for hydraulic width, depth, and velocity. And typically this is, hydraulic width is defined actually as the top width, the depth as the average depth, and the velocity as the average velocity. Okay. Now, in order to get a good estimate of that top width, we may measure it in a bunch of different places nearby, just to get a good, robust estimate of the average top width, distinguished from average depth, which is defined as simply the discharge divided by the width from the average velocity. Yeah.
So by top width, you mean like the top of the water?
The water surface. In other words, that width is what you see, the depth, what you calculate, and the velocity, what you calculate. Now, let's just write these down then and see. So typically, again, we're looking at a width relationship, and I talked about this last time. The width, depth, these are typical values. Let me show you. So these are the data from Leopold and Maddox's USGS professional paper in 1953, showing hydraulic width, mean depth, mean flow velocity, all as a function of annual mean flow. And I've kind of mixed up the words just to, make sure we remember that we're talking about all the water that came out, the total volume in a year divided by the duration of a year, in seconds in this case. And so here, hydraulic width, Y width equals 9.228 times discharge to the 0.5 power. And that exponent right there for those data, boy, that comes out nice and round, 0.500. And then, so for here, discharge goes with depth, average depth goes as discharge to the 0.3966 or about 0.4, and velocity goes as discharge to the 0.1049 or about 0.1. It's probably not news to anybody that what's that saying on a fundamental level is simply all three of those variables, all three of those values are on average increasing as you go downstream. Now, some of these relationships appear a bit more robust than others. The width, we're looking at an R squared of 0.939. Depth, we're looking at an 83% R squared, but for velocity, only at 29% R squared. So not awesome for velocity. But, not too, I don't know if you're ever going to get that awesome in R squared for an exponent in a power law that small. What's that saying is that on average, velocity streams get faster as you go downstream. It's hard to notice the same way it is with velocity, with width and depth. And it is somewhat counterintuitive because we think of headwater streams as being fast flowing and lowland streams as being more lazy. But I don't know about you, I get a little freaked out sometimes when I stick a canoe onto the Willamette and I actually see the gravel going by underneath. It's awfully fast. It's a damn big river. And it's flowing faster than I'm used to for the rivers that I typically have put canoes on. So, I don't know, maybe, there's a lot of variation there, but, now, one of the things you notice here is, let's notice after I write up something else. Conservation of mass tells me that discharge is equal to what product? It's equal to the width times the depth times the velocity. Believe it or not, that's actually a result of the conservation law. And that is your most basic conservation of mass, at least for discharge. Now I've just written up 3 different equations, one for width, one for depth, one for velocity. Let me write more general versions of these then. So that means I can substitute for width an equation like that, but I'll write it up more generally, say q to the b. And for depth, q to the c. And for velocity, q to the e. That is so I've got q over there and this over here. What does that mean for the stuff here that's not q? It means that this product has to equal 1. And this sum has to equal 1. Nothing profound there except, if I come up with 0.5 and 0.4, well, you simply know that it has to be 0.1 here. So if I know 2 of them, then I know the third. All right. And nothing terribly profound, and of course, gives us some idea of the potential magnitudes or the relationship among the magnitudes of these coefficients here as well. If I know 2, then I know all 3. Now there are other variables that are often related to discharge, like stream gradient, median bed grain diameter, hydraulic roughness. These are things that we might seek this sort of power law relationship for. And we can get decent power law relationships for some of those. The best does tend to be this width one for almost all the kinds of streams we ever look at. And that's good because we don't have another way to get it. When it's otherwise unknown, we don't have a handy way other than this sort of empirical relationship to figure out width. Because like I said, even though on some level conceptually it's not all that difficult, think, okay, if it's too wide it'll get narrower and so on. Actually getting that value is rather involved, maybe not even all that possible. In other words, we haven't really figured out a good way to do that. Not reliably anyway. Now it's robust enough to apparently apply even in the case of bedrock streams. There is a catch. Let's look at that. Let's see. That kind of work. That's good. There's the original Leopold and Maddock data in reddish squares. I plopped another data set from 1965 on there as well. The combined power law relationship is now 0.4929. You kind of wondered if Leopold and Maddock, let's not add another data point once they hit at 0.500. Here I've combined data from 10 studies, including the Leopold and Maddock and the Carlston. No, actually, I take that back, because these relationships are looking at annual mean flow. But here, these are data looking at either bankfull discharge or the 1.5-year recurrence interval flow, Q1.5. And as I said, that Q1.5 is often our best estimate. If we don't have a better estimate, that's usually our best way to figure out what bankfull discharge is going to be approximately. And so combining data from 10 studies and discharge of a couple of sorts, and channel width measured by different means as well. I mean, in here is going to include channel widths that are simply measured from topographic maps. So there's a bit of variation there. See, all these data combined are giving us, again, a power law for the next one, 0.496. I've also plotted on here just data that my student Jack Zunka collected himself using the 1.5-year recurrence interval flow and widths measured off of maps and aerial photos for these down here and a couple of them up here. This is the Mississippi, and this is like some obscure creek in Colorado or Utah. And for those, see, it's actually now not so nifty like 0.5. It's actually now like 0.636. What's up with that? Well, one thing you should probably want to know if you're looking at a bunch of data for a bunch of different streams, is how similar should I actually expect them to be? So let's think about this again. Again, we're talking about, you know, the channel width that is just right as kind of a balance of forces, if you will. But just as, you know, different flows and so on are going to have different shear stresses, different bank materials are going to have different strengths. So, you know, here I could be combining all sorts of stuff. I mean, I know just the, well, let's see, in the red crosses there, the red X's, we were very careful to choose, we were actually not so much interested in width per se, we were interested in the dimensions of meandering streams and the meander wavelengths and so on. And so we were really sticklers for choosing only streams that had no valley confinement. These are all unconfined meandering alluvial channels. And we get this steeper relationship with discharge than we see in all these data from 10 different studies, including ours. I mean, ours are part of what's giving us that trend. But we're also seeing that our data are kind of falling, I don't know, on the lower envelope-ish down here. And then once you get up here, there aren't all that many rivers in the world that are that big. This is the Mississippi. And some of these here are from Russia and in the Amazon basin. Not the Amazon itself, because the Amazon itself is braided, it's multi-threaded. A subject we'll get to talk more about next time. Okay. Here, just by the way, meander wavelength scales very nicely with channel width, almost to the power of 1, but more like 1.1. Here for all the data is 1.14. For just our data for unconfined alluvial streams, 1.08. But what I wanted to get to was to say, yeah, even for so-called bedrock streams, we do tend to find decent hydraulic geometry relationships, although we do need to be a bit careful about what we're talking about when we say bedrock. These are different streams. Big Montgomery and Karen Grand did this study. And let's see, Satsop and Willapa. Does anybody know where the Satsop is? Is that Washington? No, the Willapa is Willapa Hills in Washington. Sullivan and Larson Creek are Oregon Coast Range, Yuba, I guess that's California. Okay, so that's right down here. Satsop River, Washington, Willapa River, Washington, Sullivan, Larson Creek's Oregon, Knowles Creek, Oregon, Yuba River, California. Knowles Creek might sound familiar because we've looked at that before. Here they're looking at the open circles are the so-called alluvial reaches of these creeks and streams and so on. The solid filled circles are the so-called bedrock reaches. But what I would qualify these with is to say that the banks aren't bedrock in any of these cases. So when we say bedrock versus alluvial, we're talking about what's on the bed, not what's in the banks necessarily. Or let me qualify that. For the ones that I know and have spent a lot of time in particular Knowles Creek, and sort of by extension having spent a lot of time in the Coast Range, we're talking some other creek in the Coast Range, I'll almost guarantee you that those banks are not bedrock. The banks are made out of depositional material. And depending on how high up in the system we are, that depositional material might have been deposited by debris flows, and other places might have been deposited by the stream itself. here are the different exponents that have been fit to here, and we see they do vary quite a bit. Some of them are nice and near about 0.5, others not so much. For Knowles Creek, we've got two different values, one for less than a square kilometer, one for greater than a square kilometer, which I thought was a little bit interesting. Let me skip to that. This is Knowles Creek. You've seen it before. And specifically, I showed you these data, which are the long profiles for Knowles Creek. One thing I ought to point out is we're not looking at discharge anymore, we're actually looking at drainage area. Oh, by the way. Yeah, just sort of slip that one in there. We're not actually measuring discharge, but we're kind of inferring that discharge is going to be a power law contributing area, or vice versa. And so when we looked at Knowles Creek before, I showed you, there's a nick point in Knowles Creek. They divided two different trends at this point. So that's 1 times 10 to the minus 10 to the 6 square meters. That's a square kilometer right there. But interesting nonetheless. Go back then to their Knowles Creek data. That's about where I found the nick point right there. Now, okay. But here's something else. Often the reason that we might want to know, say in the context of channel profiles that we've been talking about the last few times, you might recall that when I had my arm twisted and derived the power law of area and contributing area and slope from saying that erosion is proportional to say say shear stress or shear stress to a power, that I slipped in a hydraulic geometry relationship for width because I had no other thing to use. And that would lead us to believe, the way I wrote it, that the coefficient is constant, the exponent is constant, and how do I therefore expect slope to vary with these other things? Here's the problem though. Aspect ratio changes with slope, according to this study in the Apennines in Italy. And in particular, there's some other graphs in this that show, as you're going through a gorge where there's been a lot of recent displacement along faults and so on, so it's relatively, it's steeper, it narrows up. So what is aspect ratio? Aspect ratio is width divided by depth. So typical values are going to be around 20 or greater often. But we see that, we get that for almost that for some of these, but bedrock channels we do kind of expect to be narrower. And if I look at these, I go, looking kind of like, looking kind of bedrocky, like probably not so, like in this case, looks like we're talking bedrock banks. In a gorge, kind of how we define a gorge, or slot canyon. So that's kind of an important caveat when you talk about hydraulic geometry relationships maybe applying to bedrock streams. Are we talking bedrock bed or bedrock banks? I've hiked down slot canyons in Utah and Arizona. The bed was always alluvial, actually. The walls were bedrock. Looking at all those, those coast range streams, some of those beds were bedrock, but pretty much all those banks are alluvial. Well, gee, that's too bad. I guess what I'll just say is that gives us something else to do. We haven't figured everything out yet. Oh well. And we'll kind of pick up there next time. and talk about what channels do on sort of a cross-sectional scale and how that implies different types of plant forms like meandering channels and braided channels. All right, have a great Monday.